Hello, and this is chapter 2. This is formal notes. So, chapter 2 has formal notes, formal notes, formal notes, a group work activity, which I'm going to go through in the formal notes section because I'm not too worried about it. I just need you to get to understand one thing. And then you can do a bonus. And then we have a problem set 3. It's brief. Problem set 1 was the longest and the hardest one. And then we have more formal notes, group work, more formal notes, group work, but also formal notes. Problem set 4 in group work, nearest neighbor, cheapest link. Problem set 5. And I think that's it. Yes. So you have 3 sections in chapter 2. And this is the formal notes for section 1. So I'm just scrolling back up to where we need to be. So in section 1, I am worried about you knowing something about knowing what weights of graphs are. I want you to know what a Hamilton cycle is. I want you to know what a Hamilton path is. I want you to know the properties of graphs that allow you to have these things or not. And I also want you to be able to argue how you know something doesn't have a Hamilton cycle. Does not have a Hamilton cycle or a path. Okay, so this is all just section 1 of chapter 2. Okay, so the total weight of this graph, notice that there's some numbers associated on these edges. So those numbers can mean almost anything. They can be number of miles between destinations, cost of transportation between destinations, many things, many things. So the total weight of this graph is the sum of all those numbers. I think that comes up to 460 without me using my calculator, but I'm going to do it anyway real quick. And no, I'm not using the computer calculator. I'm using one in my hand because it's easier. Because my computer's in tablet mode right now, so I don't have a keyboard. $468. I was so close. I need to remember. So the total weight of this graph is 468. I will be asking you later on to find total weights of paths and cycles, which is just adding up the weight of a path or a cycle. So if I wanted to find the weight of path A, B, C, D, E, A, I would add up only the edges that are in that path or cycle. 54, 98, 21, 68, and 20. So 12, 13, 21, 2, 4, 6, 11, 26. So 261. So now a Hamilton path in a graph is a path that includes every vertex. Without repeat. Okay? A Hamilton cycle is a cycle that includes every vertex without repeat. Now, let me review quickly what an Euler cycle and Euler path are. No. An Euler path. Oh, by the way, these must be connected graphs. Always, 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 always must be connected. An Euler path is a connected graph, or a graph has an Euler path if it's connected and has exactly 2 odd vertices. And an Euler cycle is connected, or a graph has an Euler cycle if it's connected and has all even vertices. Remember these because we're gonna do an activity real quick. So a helpful way to remember the difference between Euler cycles and paths and Hamilton cycles into paths is to think of each one like a virus. So Euler is every edge. So it's like the triple E virus, E. Hamilton deals specifically with vertices. So HIV. So now let's determine if each graph has a Hamilton path or cycle or an Euler path or cycle. Let's start with the Euler paths and cycles. So I'm gonna do that in blue. So in this graph we have 2, 4, 4, 4, 4, 4, 2. So this has an Euler cycle. This guy has 3 and 1. This guy is an Euler path. 3, 3, 3, 3, 4. Not Euler. Not Eulerian. But it might be Hamiltonian. We'll see. 2, 2, 4, 4, 2, 2. This is definitely an Euler cycle. This one is an Euler path because we have 1. This is 4 and 1. So we have, to convince ourselves that this is an Euler path, I'm labeling the edges. Yep, it's an Euler path, if the degrees weren't enough. And this guy is not Eulerian. Alright, I am now going to do Hamilton cycles and, in red. We have actually no properties that tell us whether or not we have a Hamilton cycle. Okay, we have no properties that tell us if we have a Hamilton path or cycle beforehand. The only way to find a to know for sure if a graph is Hamiltonian is to find a Hamilton cycle. But that doesn't mean we can't prove that they don't, okay? Okay? So here, all I need to do is hit every vertex without repeat. So this has a Hamilton cycle. It also has a Hamilton path. Okay? This guy only has a Hamilton path. This guy has a cycle and a path. This guy does not have a Hamilton cycle, but it has a Hamilton path. This guy is non-Hamiltonian. But why? We'll figure that out. This one is not Hamiltonian. Again, but why? Well, I'm going to teach you why. All right? So, that's that page. Hand tool. So let's look at some important things to remember. The existence of an Euler path or cycle tells us nothing about the existence of a Hamilton path or cycle. You can have multiple Hamilton cycles, paths, or cycles in a single graph. If a graph contains a bridge, then a Hamilton cycle is not possible because you'll end up repeating vertices. A graph can have a Hamilton path, but no Hamilton cycle. But if a graph has a Hamilton cycle, it will always have a Hamilton path. Also, I believe this is a homework question. If a graph has more than 2 vertices of degree 1, we need to remember connected here. It will definitely not have a Hamilton path. And in the next activity, I'm going to show you another way to prove that it doesn't have graphs that don't have a Hamilton cycle. So this is I do want you to at least look at it, but I'm not going to spend too much energy on it because I'm going to tell you what I want to get from this activity. So if we were to draw out every single knight's move on a chessboard, if we were only playing chess with 2 knights and drew out every possible move, we would have things that look like this. So if knight 1 started here, knights move in L shapes. So over 1, down 2. Start and stop are the edges and the lines. You can do this for the entire chessboard. Now, what makes knights one of the most powerful pieces on the board besides the pawn is that it can hit every single square in an 8x8 chessboard. So the first thing we're going to do is we're going to look at a 4x4 chessboard where all of the box squares where you can land are vertices. Now, moving like a knight from any space requires all shapes. So from this spot to here is a possible move, and from this spot to here is a possible move. I have gone ahead and drawn the 4x4 Knights tour for you, but I'm going to go ahead and go through this and draw out all the possible positions for a knight in a 4x4 chessboard, so you can see where I'm getting these lines. Obviously, pieces in the center have more places that they can go. So the degree of those vertices will be higher than ones on the outside. So you have a poorly drawn version of this. So now, when we're looking to see if something has a Knight's Tour or not, oh boy. The first step is to assume that there is a Hamilton cycle. Okay? Then, since I'm saying that there is a Hamilton cycle, I can assume that any edges that are degree 2 are in that cycle because I have to go in and out. Every vertex must have an in and an out. So that is why these are dotted. So I am assuming that these guys are in a Hamilton cycle. Now, what's happening here is that these vertices of degree 2 make their own cycle. So I can't get out from this no matter how much I try. Same with these edges of these vertices of degree 2. These edges have to be in that cycle as well. They are forming their own cycle. So I can say that there is no Hamilton cycle because the vertices of degree 2 form their own cycle. Okay? This isn't always going to help you, but in most cases it will. Now, for the rest of this activity, you're going to draw out a 5x5 Knights tour and a 6x6 Knights tour, and you're going to find the Hamilton cycles. This one has Hamilton cycles. You need to find it. Don't look it up online. This one does not. You need to show me why. Okay? So that is all I'm looking for in this group work activity. Now let's talk about the 8x8. This guy has a Hamilton cycle. Good luck finding it. Don't Google it. I know all the answers. Okay? I will give you extra credit. On either a quiz or a midterm, if you can show me that there's a Hamilton cycle in this graph. Fun fact, all even n by m actually, chessboards, when n and m are greater than 4, have Hamilton cycles. All odd n by m chessboards Do not. And I'm sure that this little bit of information is screwing with your brain because chessboards are only 8 by 8. What are you talking about? Well, we're talking about math chessboards. We're talking about extending them into infinity or shrinking them down to as small as we can. But in normal chess, it's an 8 by 8 board, and that has a Hamilton cycle in it because the knight can hit every single vertex, and it's up to you to show me that. If you can do it, I will give you bonus points. If you can't, don't worry about it. All right? Don't Google it. I have all of them memorized. So then we have problem set 3. So get on that. Get working on that. And I will make notes for section 2 soon. Good luck, and I'll be around if you need me.